Hey, pre-calc students, this is Mr. Beck. I want to talk today about two specific types of functions, linear functions and quadratic functions. Just to give you kind of like a baseline of where we're at. Chapter 1, we talked about like a lot of different individual skills. We had distance formula and midpoint. We had intercepts. We had talked about some general lines and parabolas, circles. Chapter 2, we talked about domain and the importance of domain. Then we talked about function notation, how to read it, how to look at it. Then we went increasing and decreasing functions. We talked a little bit about absolute and relative extrema. That'd be the maximums and minimums. Then we went into some of the specific functions that we talked about, mainly the parent functions, the y equals x, and how all that's translated, shifted, so on. Absolute value of graph, et cetera, et cetera. And then we went into specific applications, and we use technology to help us find the extrema. So where we're at today, as I said, we're going to be talking about two specific types of functions. This is going to be the beginning of our journey into those functions. We have linear functions, quadratic functions, and we're going to have polynomials and rationals, exponentials, and logarithmics. So that's where we're going. So the first one is our linear function. Very first question I asked is, what's your average rate of change? And that's been really the theme this entire year so far. What is average rate of change? And we know that answer is slope. The slope is average rate of change. That would be the slope of the secant line. Now, when it comes to linear functions could be secant lines. The first degree linear function is always written in the form f of x equals mx plus b, or I guess you could say b plus mx. That would be okay too. What are some real life examples? This was a student's choice, hours of homework versus brain cells lost. It only says lot, that's lost. Change of velocity versus time, that's a very, very excellent example. Lots of real world examples. If anybody has a job that has an hourly rate, that would be a linear function as well, and so on. How do we numerically, graphically, and algebraically determine if a function is increasing, decreasing, or constant? So graphically, if it's constant, we have a horizontal line. Increasing, and we read a graph from left to right. So increasing, it goes up. Decreasing, goes down left to right. Excuse me. So algebraically, we get to look at what is the slope. If the slope's positive, we have an increasing function. If the slope's negative, we have a decreasing function. Slope is 0, we have a constant function. And then numerically, when the dependent variable goes up or down, that's how we know that whether we have increasing, decreasing, or constant. So usually the dependent variable is y. So as really, probably want to be a little bit more specific on this one. So as the independent increases, so as the independent variable increases, then we look to see whether the dependent variable goes up, down, or doesn't change. So x is always going to get bigger, and that's really kind of what we mean as we go graphically from left to right. As x gets bigger, what does y do? So level 1 problem, find the average rate of change, and this one is pretty darn straightforward, that the average rate of change is going to be our slope, which is our negative 3/7. Now y-intercept obviously is 4. Most people don't have any problem with that because in pre-calculus you've been seeing that for about 4 years now. Now what I asked on this one is verify that the average rate of change over these two intervals ends up being the exact same. So f14 minus f7, average rate of change, very, very specific idea that I'm trying to get across here is average rate of change is slope. We've talked about that numerous times in class, outside of class, in the homework, etc. So our average rate of change on the interval from 7 to 14 would be that expression, which does turn out to be negative 3/7. And then we have the interval from 0 to 21. There would be f of b minus f of a over b minus a, which once again, when you simplify it, goes down to negative 3/7 as well. So this verifies that, really at least these two intervals, but pretty much every interval that we check, we should have this average rate of change of negative 3/7, because that's what slope is. So I had a couple of problems here where we first started talking about E. coli. We want to know if E. coli population of that E. coli in a petri dish, if that grows in a linear way. And the way that we would do that is we would see if we have an increase that's the constant rate of change. As we look at these two, this is an increase of 0.03 divided by 1 hour. This increase is 0.04 divided by 1 hour. This increase is 0.06 divided by 1 hour. So the main thing is it's not linear because this is not a constant change. So that's not a constant change. We need it to be a constant change in order for us to have a linear function. And this sort of makes sense because anybody who knows anything about how bacteria work, they double and then they double again, and then they double again. Basically, we have bacteria that are growing at an exponential rate, not really a linear rate. For part B, we have data below represents maximum number of heartbeats a healthy individual should have. So what we did was we at least looked at these two and then looked at these two. You can sort of follow a pattern because X changes in a nice pattern, Y is going to be decreasing in a nice pattern as well. And because of that, it looks like we should have a constant average rate of change, which we do. We see that by these two expressions, and then come up with a linear function for that. And if you notice, I put this in point slope form because point slope form is a legitimate form of a line. Moving along. Next topic I want to talk about, and really we're going to see this a lot in our chapter 3. Our chapter 3 involves a lot of business models, and as we kind of prep our students for the Calc survey, which is business calculus, we kind of like want to bring a lot of these business models in, which is also nice for the students who are going to be going on to Calc AB, because Calc AB tends to have a lot more of a science flavor, where the Calc survey has a business flavor. And it kind of like allows us to kind of introduce it to both populations. So as far as the first business model that we're going to look at is what's called straight line depreciation. What happens with straight line depreciation is we take an object that we're going to purchase for a set price. We know that eventually over time that object's value is going to be nothing. And a lot of the things that businesses do is they take a look and say, okay, this is how much it's worth now. This is how much it's going to be worth at the end, and we have what's called that straight line depreciation that they could use for tax purposes to say, okay, the value of all my stuff is this, then this, then this, then this, then this. So with that said, straight line depreciation, I mean, it's a very commonly used thing in business finance. Even when it comes to mortgages, the amount of money you have on a mortgage, you can make a straight line depreciation for that as well. So moving along, our first example is in 2018, we have a company that purchased a bulldozer for $48,000, which in my mind is a very, very cheap bulldozer. That's okay. So I'm going to label a point. We have 0, 48,000. And then we want to use straight line depreciation over 6 years. So our second coordinate is 6, 0. So at year 0, it's 48,000. At year 6, it's worth 0. Now, from that, we can come up with our average rate of change, aka slope. Our average rate of change is negative 8,000 per year. And so our linear model, if we have our negative 8,000 per year, and then our y-intercept of 48,000. So what's the implied domain? Because we're doing straight line depreciation, we're assuming that after 6 years, it's not going to be worth anything, and therefore we're going to have to replace it. So our domain is, and I'm going to really favor the set notation when it comes to a lot of the work that we do in here. That set notation is going to be very, very important because it's going to establish what our independent variable is and can you answer your problem based off of that independent variable. So it's going to be a lot of interpretation, a lot of meaning in this chapter. What's the book value after 3 years? So after 3 years, 3 is your time and time is your X value. So plug in 3 and you get 24,000. And then last but not least, what year will it have a book value of 17,500? So you set that 17,500 equal to the y value or the dependent variable and solve, and I get this number of 3.8125. Now, what does that mean? During what year? Well, in order for me to figure out what year it is, I need to know when did we start. And if we look up here, January 2018, almost 4 years later, we're going to be in the year 2020, which is our final answer. I did mention there's a big business flavor, so supply and demand. One of the nice things about supply and demand is they tend to be linear functions as well, or we could look at them as linear functions as well. Now, quantity supplied is the amount of good of an item that a company is willing and able. Anybody who knows anything about econ, willing and able is going to be kind of a very key word there. So quantity supplied, as like a price goes up, then most likely the supply is going to go up as well. If the supply goes down, the price will go down. Basically, as we move forward in the forward direction, we know that supply is always going to increase. So kind of like, let's cut to the chase, supply increases. Now demand decreases. So as the price goes up, fewer people are willing and able to purchase something, so demand is going to go down. What happens is there is this very magic number where supply crosses the demand, and that tends to be a very focus point for what we want to look at, because when we're closer to the equilibrium point, the supply and demand equal out, and we don't have an oversupply and we don't have an overdemand. Everybody tends to be a lot happier. So, first things first, find SOP and DOP. Now to find SOP and DOP, we know we could use two distinct points. Those two distinct points will help us form the line, which is what I did. First found the slope, and then used point slope form to figure out what my supply curve is. Use the 2 points to find the slope. That slope ends up being -15. And then this one, we have our y-intercept. So we came up with the two specific lines. Now, S of 75 and D of 75, I have those values there, pretty much plug it into a calculator, what you get. Then we could say the meaning. And everybody, the meaning is what we care about. We've been working with lines forever. So let's talk about the meaning of all these expressions and put math in a real world context. So when the price is $75, 3,600 phones are supplied. And then when the price is $75, 1,725, we're actually in demand. What this means in this situation, as I look at this, I'm like, there are a lot of unused phones. In fact, there are over 2 times the number of phones that are needed. So this is where, as you look at your graph, what I have here is, this is where we have 75. You can see we have an extreme oversupply in that graph. And with that oversupply in that graph, most likely the price with these cell phones would go down just so that we can meet equilibrium. Where is S&P equal 1900? So I ended up with P equals 46.67. 1900 is going to be my Y value, solve for P. And I can kind of check that. So let me erase some of these colors, all these marks that I've been making. Say, okay, 1900 is about right here. So if 1900 is about right there, does that mean that's 46.67? Yes. Yes, it does, in my opinion. So I'm all good. Or at least I feel like I'm on the right track. What's the implied domain? Now, what you should see here is that our implied domain ends up being not the entire interval. This throws a lot of students off specifically because they're like, wait a second, I can see on my graph that, let's take a look at this graph. I can see on my graph that I have a demand for values from 0 to 15 here. So why isn't 0 to 15 included? And what I'm going to suggest is, if you remember when we did problems in the beginning of chapter 2, where we had like f plus g, and we had to determine what's the overall domain, we had to look at the domain of both of those individual functions in order for us to say what the actual domain is. So because there is nothing here, the domain of supply does not exist there. Therefore, we're going to have our beginning value of 15. Now, the ending value of 190, in order for us to figure that out, we set our demand equal to 0 and solve. And so unfortunately, this isn't like very, very well defined on my, or I'm not able to be defined on this paper. So pretend that's a straight line where it crosses the x-axis is at 190. Therefore, that's our implied domain in the situation. There's no such thing as a negative supply. There's no such thing as a negative demand either. Then, where is the quantity demanded more than the quantity supplied? So as I take a look at this graph, where is my demand? So my decreasing function is bigger than my increasing function along this interval. And that's why I said from 15 to 50. Now, something that I do want to clear up a little bit, that's supposed to just be equal or not equal, because it says is more than, not is greater than or equal to. So, and then what will happen if the price of cell phones is demand is less than supplied, the price will tend to go towards equilibrium. So one of the things I do want to point out when it comes to supply and demand, a lot of econ classes have the number of items or quantity placed on the x-axis and the price placed on the y-axis. This is what we tend to call a codependent relationship. So if you're a consumer, price tends to be a independent variable that as the price goes up, people are less willing to buy something. Same thing could go up or go out there that if quantity goes up, I guess quantity, what I'm trying to say is quantity can be an independent variable as well. Sometimes one of the things you'll see me do is I'll switch between price and quantity as the independent variable, so something to pay attention to. So, moving along. Use the graph to answer the questions. Where is f of x less than or equal to g of x? What I am saying is here's where f of x is below the g of x function, which is why I said all x's where x is greater than or equal to 7. So the meaning of this is where are the y values of f less than or equal to the y values of g? We can see that's true on that region. Second, where is f of x greater than h of x? So f of x, once again, is over here. And what I'm kind of re-outlining is where that y value is bigger than the h function. So you can see for the x value is less than -4. And then last but not least, we have where is the f function in between the g and the h function. So we're saying it's going to be between there and there. So how do we define that? From -4 to the x value of -4 to 7. Now, why aren't we including -4? That's because -4, as we take a look at our graph, I'm trying to switch, -4, when we tend to look at our graph, we want to say where it's less than h of x, not equal to. And so we don't include -4 because we want less than the h function. So hopefully that was enough about linear functions. We can get into quadratic functions. When it comes to our quadratic functions, we have 3 basic forms of quadratic functions. We have ax squared plus bx plus c, which is what we call our standard form. Our vertex form, a times x minus h squared plus k, and then our intercept form, a times x minus b times x minus q. So how do we get from one form to the other? So in order to get to the intercept form, we do factor. One of the things that I'd like to point out is we have no leading coefficients in front of these x's. So if we end up factoring and have one, we would have to pull that factor out to figure out what the a value is. Now, how do you go from standard form to vertex form? It's this process of completing the square. So everything will go through standard form. Basically, if you have one of the other 2 forms, if you have vertex, you want to go to intercept, first go back to standard so that you can go to intercept. It's very, let's just say, challenging to get from vertex directly to intercept form. So it just makes more sense, multiply it out, factor, or multiply it out and complete the square. I do have some, what I would consider some formulas for this. I personally am like, don't memorize all these formulas. What are all the formulas that you really need to make sure you know? X equals negative b over 2a, pretty good to know. What this means for the vertex is when you plug that in for x, what's the y value? Then in standard form, how do we find our intercepts? The nice thing is the y-intercept is pretty straightforward there, so that's all yours. But when it comes to the x-intercepts from standard form, we usually will complete the square. Sorry, I said complete square. We usually will use quadratic formula to get our x-intercepts. Vertex form. The beauty of vertex form is it gives us all this information about the axis of symmetry and vertex very, very quickly. When it comes to the intercepts, though, not quite so helpful. So if you plug in 0, you get ah squared plus k. I'm not sure many people see that, so not as important in my mind, as well as if we set vertex form equal to 0. Yes, we do get that expression, but don't know too many people who will use that. I do think that somebody said something of this nature, and they kind of used it to do some factoring a couple years ago. But anyway, most people don't work with that. Intercept form. So when it comes to intercept form, if we have our 2 x-intercepts, what you should know is due to symmetry rules, that the distance away from the axis of symmetry is the same. So midpoint, this is our great midpoint review time. So when it comes to midpoint, then that's how I find our x value also for the vertex. That's how I find our axis of symmetry, and then we plug it in to find the y value. And then what happens if you plug in 0? Yes, you get that expression. Is that helpful for you? Maybe. Kind of nice to know that all you have to do is multiply those three together and you're fine. More specifically, one of the benefits of intercept form is you get your x-intercept very quickly. So we have ways of being able to get all the information here. What I do want to point out is that like in Algebra 1 and Algebra 2, you spend an entire chapter on quadratics where we have just one section on quadratics. So what this means is we're expecting that you can remember a lot of those individual things that you learned from Algebra 2. That doesn't mean that everything is going to be completely fresh in your mind. That's the point of pre-calculus. We're going to make sure that it's fresher in your mind as you move forward. So what I did with this level 1 problem here was I ended up changing that minus to a plus, mainly because I wanted to see this more in a factorable form to say, okay, what's the best way of approaching this one? So I changed it to a plus. I did that for one class, where other classes I kept it as a minus. The problem in essence doesn't really matter. It's just what do you want to do with all this information? So by changing it to a plus, okay, let's work with it. And the reason why I did was because it was factorable. So what this means is getting this in an intercept form ends up being a little bit more beneficial. How do we find the vertex? Vertex, if we take halfway in between our two x-intercepts, halfway in between 6 and 2 is 4. So there you go, x equals 4. And then we could plug it in to find our y value of -4. I don't always ask this question, but does this open up or down? It opens up. And why I care about that is because since this is a quadratic that opens up, this graph has an absolute minimum, which helps us also establish the range is going to be from the y value of the vertex all the way on up to infinity. Domain of this is all real numbers. I realize I'm kind of out of order here, but this is a polynomial function, and every single polynomial function is smooth and continuous everywhere. Therefore, that means that our domain is going to be all real numbers. So, intercepts. What I'm going to do is look first of all at the y-intercept that comes from standard form, because that helps me find my y-intercept very quickly. And then our x-intercepts, we have intercept form, hence the whole intercept idea. The intercept form will get us our x-intercepts very quickly as well. So every form has a specific purpose. On this level 2 problem, what I did was I ended up completing the square just to kind of reestablish some of those individual skills. If you remember, when you complete the square, you have to factor the leading coefficient out of the both x terms. And then to complete the square, this is going to be b over 2 squared. I know it's kind of hard to see right there. I'll change out of highlighter mode here if I want to do any more work. Now, one of the things that I did challenge my students to do in class today was, and yesterday, if I take this negative, if I add 9/4 to complete the square, it's really being multiplied by that -2 as well. So instead of adding -2 times 9/4 to both sides, what I like to do is I add it and subtract it at the same time so that you end up having that gain of 0. This is kind of a stronger mathematical thought, because what you're doing is you're changing it in a specific way. By adding and subtracting the same value, you're not changing it, but you're just changing what it looks like. So from that, we get completing the square, we get this into vertex form, which allows us to find our vertex very, very easily. Now, why does this open down? It opens down because we have a negative leading coefficient. And then our y-intercept I did find from up here, and our x-intercepts I just used quadratic formula on this slide to get the x-intercepts. Domain is -infinity to infinity, because once again this is a polynomial function which has a domain of all real numbers. Now the range, something that I really want you guys to focus on is to make sure you always go from the smallest value to the largest value on the range. So if our largest value is the y value of 31/2, our smallest value is -infinity. So therefore we're saying -infinity to 31/2. Do not say 31/2 to -infinity, because that does not make any sense whatsoever. All right, doing some graphing. This one is in a factorable form, so we can graph this, and if we really needed to, we could use the pattern. So once we establish where our vertex is, we can go out 1, up 1, out 2, up 4. Sorry, yeah, 4, which should end up being right here. You can see those points are also on the parabola. What I like to do here is I like to find my vertex. So my vertex has to be one of the specific points, and then both intercepts. And let me do this in highlighting. Both x-intercepts, and then the y-intercept, and it's what I call the symmetric point. The symmetric point is on the other side of the axis of symmetry. So how did I get all this information? I first factored it, and by factoring it, I was able to figure out what my axis of symmetry is by going halfway through. After doing so, found f of that, and I got -9/4. And then which gives me the vertex of 5/2, -9/4. My intercepts, I can get y-intercept and x-intercepts from these equations and put them on the graph. Now, does this have an absolute max or an absolute min? Because this opens up, it's going to have an absolute min. And then something that I added to this is on the interval from -infinity to 5/2, our y value gets smaller. And then from 5/2 on, our y value gets larger. So we decrease, then we increase. This level 3 problem did something a little bit different because this is not factorable. What I decided to do instead was just said, hey, let's do x equals -b/2a. One of the things that I'm really hoping for you guys is that you have mathematical flexibility. You don't necessarily have to do things a certain way, but the problem lends itself for you to say, I should do it this way. Your challenge is, can you figure out how to approach the problem based on what's given to you? So in this case, I did x equals -b/2a. Plugged it in to get the y value of 13/2, which gives me my vertex. Kind of an ugly number, but that is okay with me. Y-intercept is f of 0. And then to find the x-intercepts, I went back to the original, or really I have my function here. I use quadratic formula to find my x-intercepts. I always want you to please place 5 dots on the graph. So those 5 dots typically are your 2 x-intercepts, if you have them, your y-intercept and symmetric point, and its vertex. I'm not sure if you remember discriminant of a quadratic. Discriminant of a quadratic is b squared minus 4ac. If that's positive, you have 2 real solutions. If that's negative, you have no real solutions, which translates into no x-intercepts. And then if it equals 0, you have 1 real solution, and that's because the vertex is on the x-axis. So first thing I did on this level 3 problem was I looked and graphed both of these. And both of these can be graphed using the shifting, dilating, and reflecting that we learned officially at the end of last chapter. So if I graph both of these, my question now asks me, where is f of x greater than g of x? So where, as I look at this, is where is my parabola? So where is my parabola greater than my line? My parabola is greater than the line on this interval, all the way from here up until here. It's right here where it cuts off. What are the x values where that occurs? That occurs from -4 to 2. And it's just greater than because of this sign right here. That sign says I want to know where the y values of my parabola are greater than the y values of my line. Algebraically, how do we do this? We can just plug in both expressions, bring everything to one side. I divided by -1 just to make it more easily factored. And then what I would have to do is I would have to do kind of a number line test. I have this expression. This expression says, where is this less than 0? Now, if I check intervals from or between my zeros, because I know that's where it equals 0, everything else is either greater than 0 or less than 0. We sort of like see that in a lot of the work that we do at the beginning, where we kind of compared everything to positive, negative, and 0. That's why I asked that question up here. Going back a little bit more. So what I did was I established where it equaled 0, and then everything in this region is a negative times a negative. Everything in here is a positive times a negative. Everything in here is a positive times a positive. What that tells me is where, or for what x values, is that expression less than 0? It's everything between -4 and 2. Next problem, suppose you know a quadratic function has a specific vertex and goes through a point. How do we find the equation of f? Since we know the vertex, let's start off with vertex form. Plug in what we know. Our vertex is -3, 2. And then it goes through the point 1, -6. So what we could do is we could substitute -6 for y, 1 for x, solve for a. And then once we solve for a, we can put it back into that initial quadratic form. For part B, this quadratic function has given zeros because I'm given these two zeros. In order for me to find the equation, I'm going to set it up as intercept form, like you see here. And then, once again, you plug in the given coordinate to figure out what your a value is. And so this ends up being a very ugly looking expression, but that's okay. Ugly expressions are expressions too. Last but not least, we start talking about word problems involving quadratics. Suppose a manufacturer of gas dryer has found that when the price goes up, the revenue is given by that equation. So, or the price changes, then the revenue is going to change in this manner. So it's a quadratic manner. So to maximize our revenue, what I did was I first established to maximize revenue. That means that I want to know where I have my maximum revenue, aka the vertex. So to find the vertex, I did -b over 2a. It said $500 is my price to maximize my revenue. Now to find the maximum revenue, let's plug 500 into the R function, which stands for revenue. So R of 500 ends up being $1 million. And now for, as we look at part C, in order for the company to establish, to see what how the company is going to prevent revenue from becoming negative, which means, I mean, you really can't have negative revenue, but for revenue to not be negative, you need to end up with that parabola greater than 0. To answer that, you want to say it occurs between these two given x values. Our level 4 problem here is we have daily revenue achieved by selling X boxes of candy. We have a function for that, but we also have a cost function. So the first question is, how many boxes must the firm sell to maximize the revenue? So our goal for that is, hey, maximum revenue means we're looking at vertex one more time. So to find the vertex, if you notice, I did x equals -b over 2a, which gave me 118.75. Now we can't have 0.75 boxes, so we are going to round to the number that makes more sense. And if you do kind of like a micro scale, 119 is going to be slightly above the x value of 118. So how about the y value of 119 is above the x value of 118. That's just due to the symmetry among the parabola. And then what is the maximum revenue? Plug it in and see what we get. For part C, we're changing our situation. We're saying, okay, profit is revenue minus costs. Once again, I mentioned that this chapter has a strong business flavor to it. So if we have revenue minus cost to get profit, we just really subtract our two equations together and we get this. Followed by part D that says, how many boxes must the company sell to maximize profit? So I take my profit equation and I, one more time, find the vertex. Once I found the vertex, I get the x value of 103.125 boxes, which we round down. And the reason why we're rounding down in this case is because this is going to be closer to 103. So if we look at the parabola, we know that it should be a lot closer to 103 as opposed to just a little bit above it. And then to maximize my profit, or what is my maximum profit? I plugged 103 in. I know that question wasn't asked, but it was something that I was kind of curious about. So even though the revenue is $564-ish, we have a profit of only $179. So we're not really gaining a whole lot of money off of this, even though our revenue makes it look like we have a lot. And this happens a lot. So I think I said a lot too many times, which means it is time for me to go. Thanks, pre-cal kids. Have an amazing day.